Let's look at the simple example you can use a VNA for. When you buy a capacitor, you get an inductor for free. This parasitic element comes mainly from the connection wires. Thus, in reality, the capacitor is a series resonance circuit consisting of R, L and C. But can we also quantify the parasitic elements with numbers so that we can build a spice model out of them? Sure. First of all, let's start with the calibration again. This time, we choose the frequency range from 300 kHz to 300 MHz. We will perform a simple one-port measurement, which means 3 calibration measurements are enough. This time, we perform a calibration without the test cable. So let's calibrate short, open and match at port 1 and activate the calibration. Before we look at the capacitor, I would like to demonstrate what happens if the calibration is done incorrectly. And now connect the test cable from the last video to port 1. You can see the clockwise rotation, which is caused by the cable length. But now I increase the stop frequency to 1 GHz. After a calibration, you should never change such settings. What you see here is that some measurement points are located outside the Smith chart. This would mean a negative real part, which we definitely don't have. The nasty thing about the wrong calibration is that the result usually doesn't look that wrong. Here, for instance, I measured a wavelength at 617 MHz, which corresponds to a line length of about 32 cm, which is more or less correct. But now let's plug in our capacitor. Once again, we see the wrong calibration here. Therefore, let's set the stop frequency back to 300 MHz. As a rule, our measuring points usually rotate clockwise. Low measuring points are therefore located to the short circuit point. But shouldn't the capacitor start at the open circuit point? Yes, it does, but we just don't measure it. At around 300 kHz, there is already the first resonance point. Every time we cross this horizontal axis, it means resonance. After all, resonance means nothing else than that the imaginary parts cancel each other out. Each series resonance is followed by a parallel resonance, and vice versa. In the impedance curve, this means a steady up and down. But believe me, measuring anything above the first resonance requires really a high level of measurement skill. We can now also export this measurement data. The industrial standard file format for this is called Touchstone. We only need to export S11. Whether we select Hertz or Gigahertz as the unit doesn't make much difference. With the format, on the other hand, I would recommend real and imaginary parts. Because we are saving only one port, the file extension is called S1P. If we would save 2 ports in an S2P file, we would have already 4 S parameters saved. With a 4-port measurement, there would be 16 S parameters. Now, let's take a look at the exported Touchstone file. The format is very simple. The first line specifies the header. It says the unit of the first column is gigahertz. Each line in the file is a measuring point, so we can scroll down to 300 MHz, which is the measuring point 4501. The frequency sweep here is linear. I haven't found the logarithmic sweep for the LibreVNA yet. We have stored S parameters, but we can easily convert them into the familiar Z parameters. Columns 2 and 3 are linked and indicate real and imaginary part of the measuring point in a 50 ohm system. Many simulation programs such as KeySet ADS can natively handle Touchstone files, but also with MATLAB or Python, the import is quite simple. Let's just quickly write ourselves such a script. The first MATLAB commands are just for initialization, you can ignore them. The import itself takes place with a one-liner. In the MATLAB documentation, everything is explained again very well. The import variable contains the entire Touchstone file now. Column 1 contains the information about the frequency. We have to multiply this by 10 to the power of 9 since we have specified gigahertz as the unit. S11 is stored in column 2 and 3 as real and imaginary part. We must manipulate these columns accordingly. S11 is equivalent to the reflection factor gamma, so we can calculate the impedance from it. And now we just need to have the data plotted. For the impedance, we usually plot the absolute value logarithmically. That doesn't look so bad already. Perhaps a phase plot would be nice. For this, we only need to calculate the arctangent of the imaginary part divided by the real part. Finally, we convert from radians to degrees. Great, I guess the two measuring points here just can't decide. Okay, now let's create a lumped element model from this measurement file. For this, we simply rebuild the RLC series resonance circuit. We can read the value for the parasitic resistance from the impedance plot since it acts alone at the resonance point. For the inductance, let's just try, let's say, 10 nanohenry. The capacitor value is 680 nanofarad according to the datasheet. Now, I just add these values together as complex impedances and I have to complete the plots with our model. The result already looks not so bad, maybe a little more inductance. Yes, that fits well. But strictly speaking, we actually didn't calibrate quite right. We have measured the capacitor including its SMA connector, so the reference plane is not set correctly, but this is not even possible with a simple calibration kit on the market. Therefore, a so-called port extension is carried out. For this, we only connect the SMA connector itself to the VNA. The port extension function now recalculates the measurement points back to the open circuit point. If we now measure the capacitor again and export its data as a touchstone file, we get a slightly shifted impedance curve in MATLAB. This in turn means slightly less inductance, exactly what we wanted to achieve with the port extension.